Hi, I welcome you all to my keynote talk titled Abstracting Latent Space Through Deep Learning. And I am very grateful for the organizing committee of the 7th edition of International Conference on Optimization and Applications, ICOA2021, for inviting me for this keynote lecture. To start with, I introduce the concept of computer vision, which is pretty well-known concept at the present day. So computer vision is to implement the components of vision capture in forms of image and video, and then processing the same to the computational techniques or algorithms and generating the inference out of that information. So this is very similar to the process our biological sensory and processing system works through our vision sensors and then through processing in the brain or the spinal cord of our biological world. And the same process, if we want to do in the artificial agents through computational techniques, this is commonly called as computer vision. So in order to understand the information hidden in the given image or the video, or to understand the pattern, to recognize the pattern, to classify the pattern, which are commonly known as object detection, segmentation, understanding the image or image captioning, we can adopt two basic techniques. The first one is called the supervised learning. So in the case of supervised learning, we develop the learning paradigm and we try to capture the knowledge, the domain knowledge, by supplying some information which is termed as training data, which consists of the given information and the corresponding label. So my system tries to find the function or tries to generate a function which can correctly abstract the pattern from the given image, and it can also evaluate the error because the label is already supplied to me. So evaluating the error, the model can reduce the error, and that's way it becomes a better and better classifier or a recognizer. And this process is called supervised learning. And the example what I show here, you can see that I supply my network with a number of handwritten digits, and these handwritten digits, all the digits are labeled. So my network learns the various patterns for the different categories or different labels of the digits and tries to formulate that and tries to develop the function which can map from a digit to its label. And once I do that, then I tell that I have learned the model and I have abstracted the knowledge. And then this model can work fine for any given handwritten input numbers. And this can be very robust. We can imbibe that in also in a sort of system which can identify objects of much more complexity. Like we can actually have a robot moving in my garden and can understand that hey, this is a plant, this is a flower, this is a leaf, this is a stem, right? Or this is an insect, or this is the grass of the garden, and so on. So this particular process of learning is of very vital importance in the present building up of computer vision systems, which can autonomously perform or guide certain actions. The other technique for abstracting the image information is called unsupervised learning. So in the unsupervised learning, what we try to do is that we don't have the labels. We don't have prior labeled information which helps me to abstract the knowledge of the domain. So what I do, I have data, right? I have images of different objects, right? And what I try to do here is that we try to extract the features of the supplied samples, and we construct a feature space. So the feature space is something which is being shown in the diagrams. We're having the feature axis, and so the given features forms the axis of this particular space. And when I estimate the feature values of the given data sample, or the given image, or the given object, right, I can, based on its feature value, the object comes in a particular can be conceptualized at a particular point in the feature space. Right, and what I do, I have supplied with a large samples of objects or large number of images from where we extract the features, and then we try to plot the features in the feature space. Once we plot the features in the feature space, we can easily generate a metric which is called a distance metric, and this distance metric tries to estimate the 2 points in the feature space, how close they are or how far they are. If the points in the feature space, as I show in the diagram in the top right, are very close to each other, then we tell that these points are the part of the same cluster. Whereas the points which are far away from each other are known as the points from different clusters. So by this, we actually form the clusters of data points once they're projected on the feature space, and that can give us a notion that hey, these data elements are pretty similar to each other, which are the part of the same cluster, and the data elements which are far apart or which are which are the part of different clusters, they will be dissimilar objects. And that's the way we try to distinguish between objects such as whether this is a man or this is a cow, or whether this is a apple or this is a banana. So this is the way we try to distinguish the objects, and this is also a learning process. There are certain techniques by which we can understand the feature space better, and we can optimize the feature space better. And the most commonly known technique is the PCA, Principal Component Analysis, which tries to generate the feature space which maximizes the variance in my data space, which helps me to create more distinct clusters. So in a nutshell, sometimes we have to do a sort of transformation from the fundamental feature space to the eigen value based feature space, which is the PCA, to generate the clusters in a better way. And this is also an important way of understanding the domain in terms of computer vision. So if we summarize the two techniques, that is the supervised learning and unsupervised learning, we can summarize that supervised learning has the data with labels, and supervised learning doesn't have data with label, they only have data. The supervised learning generates a function, okay, which tries to map the data with its label, and that's called the learning process. Okay, and for that we use the supplied data and their labels. Whereas in the case of unsupervised learning, we try to explode the data space in terms of its feature and tries to abstract the knowledge in my data, right? And that helps to differentiate whether the two data are similar or dissimilar to each other. The examples of supervised learning are classification, object detection, semantic segmentation, image captioning in the context of image and video processing. Whereas in the case of unsupervised learning, it's basically clustering and it's basically some sort of feature learning, okay, to understand the features of the objects. The primary content of this lecture will be focusing on unsupervised learning because the latent space exploration, which is one kind of feature space analysis, is performed in this domain of learning, and that's the context of my today's lecture. So what I will touch upon are the various techniques of unsupervised learning or latent space exploration, and we will study or we will learn the various techniques like autoencoders, variational autoencoders, and generative adversarial networks. So this is a task I give to all of you, that let's try to find out of the three faces, A, B, and C, which face is a fake. Fake means that it is not the face of a real person. It is a face which has been generated by some computational technique in an artificial way. So to understand how such faces can be generated, let's try to understand the basics of generative modeling. So generative modeling try to understand a sort of distribution of the data, right? Given samples, we try to understand that what are the key contribution of the samples in this distribution, and that is called the density estimation. So for a given images, we can try to find that what is the information space the samples are more concentrated. And now if we try to tweak this particular distribution of the sample, what we try to generate is a different kind of information, right? And that's what is actually done. So using the data, using the input samples, okay, we try to understand its distribution and try to find what is the role of this particular distribution pattern in the generating the object information. And then we can actually generate the various type of other objects by modulating this distribution, right? If I modulate the distribution slightly in a very small manner, the objects will be very similar, but they're generated through artificial means because I didn't supply the data to that, to my algorithm, right? My algorithm tweaks with the distribution and generates a sort of a new distribution which is which is actually new samples. But if the distribution is very similar, only a minor modulation has been done, then the generated objects are very similar. But if we try to tweak the distribution to a much more greater extent, then what we have the objects which are very dissimilar to each other, right? And that's the way what the generative model principally works. I didn't still explain that how we try to tweak the distribution or how we understand the distribution. What I try to tell you here is that this is the basic concept of generative modeling. So if we go back to my 3 pictures what I showed a couple of slides before, those pictures are all generated through these generative models, which means that none of these pictures are captured from real individuals. So we taken some pictures of individuals and try to understand the distribution, and then we generate many more by just changing the distribution either with a small fraction or with a large fraction. Okay, and that's the way we can really generate a lot of these fake images. And this is actually is a very important aspect of research nowadays, to understand that whether a given image is being generated by a fake process or it's a real image. And that's called deepfakes, which is now a bit buzzword, okay, in the domain of computer vision and cybersecurity. Now we go to the another aspect of the generative models. Okay, that is how we can use it for some good reasons. Okay, so the example what I show here is that the generative model tries to understand the distribution, and if we understand the distribution, we can easily find that what is the outlier in a given input, because the distribution of these scenarios are pretty well known to me. And now in the runtime, if I find that there is an outlier in the distribution, when analyzing the distribution, then I can tell that here something wrong is happening. And this is the way we can detect anomaly in the real-time scenarios. Okay, so the example what I show here is that you can analyze the distribution of a highway road when it is perfectly good, right? But on the highway, several incidents can happen, right? There can be an accidental fall of an object like an aeroplane on the highway. There may be a drastic change in the vision or the environment or the lighting conditions in the highway due to rain, due to fog, okay, due to cloud, all of this. And there may be some sort of pedestrian movements which are unlawful on the highway. So this is a good way to understanding the distribution, and then trying to find the deviation or the outlier or the anomaly in the distribution will give us a good way to detect this type of sudden changes in my video information. To go into the deeper of this concept, I now introduce the concept of latent variable or latent variable models. What are those? Okay, so there are 2 very fundamental models which works with the latent variables, and they are known as autoencoders and generative adversarial network. We will have some good discussion on both of this model, how they work, what are their, how we can design these models, and how we can make these models to act upon. To understand what is a latent variable, let us go through a very old story. So the story goes like this, that there are prisoners in the prison who are on one side of the wall, and there are the prison keepers or the people who are guards of the prison, they're on the other side of the wall, and the illumination of the prison comes from from one side of the wall, and the light comes, or the prisoners sees the other side of the wall. Okay, so what is actually happening here is that the prison guards are carrying some objects and they're moving, right? But due to the wall, the prison guards are not visible to the prisoners. The prisoners are only seeing due to the light which is falling upon the objects and just hitting the wall, which the prisoners are viewing. The prisoners feel that these objects are moving, but actually these objects are not. They are being carried upon by the prison guards, right? And these prison guards are a sort of latent variable which are not being recognized or being understood at the first-hand information level. But they are so important to understand what is actually happening. And that's exactly what is the latent variable in the context of image or of video, which means that there are features, okay, which can represent the information, but those features are a bit deeply hidden, okay, in the image or the video, and they are not being apparent at the first hand. So to understand those features, we can and if we can abstract those features, the good point is this, that you can have a lower abstraction space, and probably you can regenerate the same information with the latent features in a much lower dimension, using a much lower dimension of your feature space, right? And that's what is the concept of latent variable. Let's look into the first activity in this particular direction, which is an autoencoder. So what is an autoencoder? Autoencoder has two processes. One is called the encoder and one is called the decoder. So the encoder is something that you give me X, right? I will encode it and I will generate H, where H is normally of much lower dimension than X. And the decoder function accepts H and generates G of H, which we can assume as R, and this R should be very close to X. If R is very close to X or exactly same as X, then we have a very low error in the that means we have a low error or we have a zero error in the entire process of encoding and decoding. But the main idea or the main advantage of this particular autoencoder is that you can represent H, which is an encoding of X in a much smaller dimension than X, and you can again come back to R, which is X or very close to X, through a decoding process. So you don't need to store X. Okay? We can store a much reduced dimension or reduced representation of X, and still we can regenerate the X, or we can regenerate something R which is very close to X or which is actually X through the decoding process. And that's the entire game of the autoencoder in a very summarized way. So I show an example here which tells that, hey, you start with a handwritten image of a number, and we try to reduce the feature space. So the reduction in the size of the bar actually is a sort of dimensional reduction, and we stop somewhere in the Z, which is the most condensed representation of the feature space, so that we can again start from Z and we can regenerate X or very close to X to the decoding process. Right, so this part, which is from the initial X to the coming to the most what I can say, the most useful latent space, or the reduced latent space, which is sufficient to generate the same object or the same input once again through the decoding process, is actually the latent space representation, or the latent representation of your input. So here I show the full scenario where I show that I start with an input image, I convert it to the latent space representation Z through the encoding process, and through the decoding process I generate the approximate of X, or very close to of X, which is X kappa. And obviously there is a loss function which measures the difference between the X and X kappa. Okay, and obviously the better way of representation is that to have this loss function, okay, or this error value within a particular limit as low as possible. So this is an example. So I take a smiling face and I encode it, and the encoder latent space is something very different, right? What we observe is something like the intensity patterns, edge patterns, texture patterns, but what latent space is storing is something different type of feature values, right? And that's what is the latent space abstraction. So it shows a sort of feature space, okay, which is something defined in terms of smile, in terms of skin tone, in terms of gender, in terms of beard, in terms of glasses and hair color. And then it gives the, okay, in some normalization scale, it gives the value of these particular features. And this is how we store this particular image information in the latent space. And then we try to decode it, right? And we again regenerate the same image, or very nearly the same image. The other way is a stepwise progress. So we don't drastically reduce from the dimension d to the k at step 1. What we do, we do a gradual reduction in the feature space, and we go from dimension d to dimension p, which is a little bit less than d, and then to t, and then to s, and then to k, right? And we have a gradual step process, which is called a deep under compute autoencoders, under complete autoencoders, okay? And then we actually follow the same process in the decoding. So we gradually step up in the feature space. So this example shows that the dimensionality reduction to the latent space, how it performs good or how it can perform bad. So we show that uh, from left to right, if the first image is a heavily reduced latent space, so it's a 2D latent space, whereas the next is a little bit better or a higher dimensional latent space, which is 5D latent space. And obviously we have the ground truth. So we see that the latent space, which is having a more dimension, when we try to decode it, it will have a very nearly same as the ground truth as an input, right? Whereas if we reduce the dimension heavily, right, when we try to decode it, we can find that the errors are a bit high. So that's also a sort of optimization you need to carry out, that what is the level I try to represent, or what is the dimension I try to represent the latent space, so that my decoding error is not pretty high. But it depends on the type of application you are trying to exploit this particular phenomenon. So now I will briefly introduce a little variant of these autoencoders, which are called variational autoencoders. Variational autoencoders tries to modulate the decoding phenomenon, or to try to modulate the latent space we generate through the encoding phenomenon, and it tries to through the modulation of latent space, okay, the decoding process generates a certain new image information, right? And that is a generative model, we can tell. Though the decoding itself is a generative model, but when we try to impart a variation in the latent space from the initial latent space, what we try to generate a variation in the output also, right? And that's the way we can generate a lot of my data, right? And it can be very well used in the procedure of the data augmentation, what we knew, or data normal, okay, or reducing the bias in the data, right, by generating augmenting the image data, right? And that's what is called variational autoencoders. They try to impart some statistical variations in the latent space, right, and to produce some new data which may be very close to the actual data, depending on how much it varied statistical parameters, or maybe a larger variation from your latent space representation, depending that whether I have varied the parameter to a larger extent. So here I show a little example which actually tells that if we try to do a variation in the latent space using the variational autoencoders, okay, how I can generate the images, okay, which are varying with my initial input image. And that's the example what has been shown. So we see that the latent space has been a little bit tweaked. Okay, so if you see the parameters of the latent space, which is the initial sample, which is the upper example, and the lower example where we had done certain variations, imparted some variations in the latent feature space, and then we do the decoding. We find that the decoding of the after we do the variation latent space, the decoded image will be having a certain variation as that of the decoded image, which is just decoded from the initial latent space. The other good example is that, okay, look at this particular images where we have two fundamental features like smile and head pose. So we can have a variation in both the feature values, or both the features, right? And we can generate a lot of images which are having a different combinations of smile and head poses. And this is a good example of data augmentation, which we can do using the variational autoencoders, and we can the latent space perturbation. The other good way of applying this variational autoencoder is to reduce the bias in my input data set, or sometimes it is also called as imbalanced data set, handling imbalanced data set. What does it mean? It means when I am trying to train my model for the various classes of images, many of the times we don't have the equal proportion of all the classes. So what happens is that my model is biased to a particular class, and for the other classes, for the test input of other classes, it might give a high error. So for example, what I show here is that my input data set or image set consists of the images from a particular ethnic class and for a particular emotion. But when I try to test my model, it can be coming from, the images can come from, face images can come from various ethnic groups, and as well as they can have various emotions. So can we take the help of variational autoencoders to modulate this and can generate a large number of images through the modulation, through the perturbation, so that my training set is pretty good. So what I show here below is the distribution curve, which is Gaussian in nature and which has a sharp peak, so which means that the samples are mostly concentrated in a particular region of my domain. Now if I try to flatten it with my perturbation in the latent space, then I can probably get a equal distribution of the samples in the entire space, and that is represented by the darker line, which represents a more flattened Gaussian curve, right? And that's what it generates. So that particular perturbation leads to the images which can be of different ethnicity and different emotions. To summarize the activities which we can perform through variational autoencoder, we can see that it is obviously a compressed representation, and it is unsupervised because we don't have any sort of label of the data. But we can do a bit of reparameterization of the latent space, which actually does a perturbation in the feature space, and it can generate some new samples from an input, from a given input. Right? That's why it can be very heavily used in data augmentation in preparing the training set. Next, we will discuss about the generative adversarial network, which is also a generative network, and we will see that how two networks works in a competitive manner to understand the latent feature space, and that can also help to understand as well as generate new samples from a given set of data. So in a very summarized way, the generative adversarial network are represented by two networks. One is called the generator network and one is the discriminator network. So generator network tries to come close to a given input through the learning phenomenon, through a gradual learning phenomenon of reducing the error between its generated object and a given object. The discriminator is a sort of constraint which tells the generator that your generated output is not same as the input. So in fact, in this process, the discriminator helps to make the generator more knowledgeable. So the icons were represented as something like a generator is a sort of thief and discriminator is a police. So generators tries to generate the image which is actually the fake image, because it is not actually the real input captured image, and the discriminator is a watchdog, it's a police which tells that, hey, you are wrong, you are not okay, you are being caught that you have you've generated a fake image. But in this process, the generator becomes better and better, its logic becomes better and better, and ultimately it tries to match the input image where we cannot find the difference. And then we can tell that the generator has learned the latent space of the input image. The process, as I told, can be described by this particular illustration, which tells that there is a generator which can initially start from the noise, okay, just to have a very even distribution without any bias, okay, and then it tries to come up with the understanding of the feature space of the input image with the help of the discriminator. In fact, the discriminator is helping the generator to by letting know that how much it differs from the input image, to adjust its network, right, and try to generate closer and closer output as that of the input image. And in that process, it tries to adjust its network so that it can really generate the same image as that of the input. So once the training of the generator is done, then the generator can actually takes an abstraction of the latent space, right, and now it can generate a new data or new images, okay, with certain tweaking of the latent space, right, and either it can generate the same image automatically, or if I try to tweak the generator a bit, we can generate different images which can be very close to as that of the input image or a little bit different from that of the input image. So to give a very simple understanding of this generator and discriminator, let's try to focus on discriminator first. It's also a neural network, and the way it works is that it tries to define a threshold, okay, at its output, and if it finds that the value what is generated, what is supplied by the generator, is less than a threshold, it tells that, hey, you are wrong, right? If it goes above a threshold, it tells that, hey, you were right, okay? Whereas the purpose of the generator is try to understand that where it has gone wrong, right? And it tries to adjust the weights of the network, right, accordingly, so that the weights which works on the input can generate an output, okay, which can be closer and closer as that the discriminator accepts. So there is a very interesting case which is also called CycleGAN, which is actually trying to work between two domains. So we see that we have a horse and we have a zebra, and whether we can generate a horse which has a pattern of zebra. So what it does that it tries to start from a particular domain, right? It tries to generate a particular domain, and then it tries to put it to the discriminator of another domain, right? And try to find that what's the difference between the two domains, how much the difference is there, right? And how the difference can be closed enough, okay, so that we can actually have an mix of the two domains, right? And so there is a backward and the forward path between the generator and okay, of domain, okay, which moves from domain 1 to domain 2, and then there is a discriminator of each of the domains, which tries to tell that hey, you are not still very close to my domain. So that's the way the CycleGAN can work and can gather the information from cross domains to generate the data or the information which can be composition of two domains. And this is also very helpful in generating a lot of cross information, and as well as it can generate a lot of fakes, okay, in the interdomain dependency relationship. So to summarize, that we have discussed about the latent space representation and its exploitation through the autoencoders and variational autoencoders and generative adversarial networks. The significance of autoencoders or variational autoencoders is that it tries to diminish, it tries to reduce the dimension of representation, right? And many of the times this can work as similarly as the feature space compression or feature space reduction, which is done in traditional machine learning to the techniques like PCA and LDA. It works very well for the deep networks. Okay, so we can actually apply the deep networks or the convolution on the compressed feature space or the latent feature space defined by the autoencoder. And that's the way you actually reduce the time of because as the feature space is reduced, you can have a reduction in the time of the training. That's the way it helps a deep network. And generative adversarial network is basically trying to, again, a very unsupervised, very good way in the domain of unsupervised learning, where we don't know anything about our input information, but we are trying to generate your own information and trying to find that how much it is close to the input information, and by the process you are gathering the information of your input of your input image, right? And that's where you can actually generate a representation learning again, right? And through the representation learning, you can now work on the different variations of that, and you can again use it for generating a lot of data in the domain of data augmentation, or you can also use it to understanding the domain in a better way. So these are some of the good references which you can look forward of some of the phenomenal works which has been done in the domain of autoencoder, autoencoders, and the latent space visualization or latent space construction, and the generative adversarial networks. So thank you all for listening to me, and I hope that I have discussed some very important aspects of unsupervised learning using the understanding of latent space, and I hope that some of you will be motivated, if not working already, to start work in this particular exciting domain of computer vision and deep networks. For any further communication, please email me at my email address secaks@caluniv.ac.in, and I will be very happy to connect and collaborate with you all. Thank you once again.